Okay, we look at solving systems of equations algebraically by substitution. Okay, so you should be familiar with solving graphically, where you graph them and see where they graph the equation and see where they intersect. Okay, now an algebraic method is by substitution. Okay, and I go through a quick example here with you to start off with. Okay, if we're given this system, 3x plus 2y equals 13 and y equals negative 1, well, hopefully we could recognize there that if we see that y equals negative 1, we can substitute that into the other equation. Okay, and then if we do that, okay, we have 3x plus 2 times negative 1 equals 13. Okay, and then solving that for x, okay, we have 3x minus 2 equals 13. We add the 2 to get 3x equals 15, and then divide by 5 to get x equals 5. So what that's telling us is the solution would be 5, negative 1. Okay, graphically, it would mean that this line, 3x plus 2y equals 13, and the line y equals negative 1 intersect at the point 5, negative 1. Okay, now previously we were given a system, and the graphical solution was 2, negative 3. Now this one matches up. I'm going to be switching back and forth here. That matches up. Y equals 2x minus 7 and y equals negative 3x plus 3. That was from a previous lesson, solving graphically. Okay, so we have this system. When we solved it graphically, we saw they intersected at the point 2, negative 3. Okay, so we could graph those lines and solve graphically. Now what we're doing is we're going to take that same system and solve it algebraically. Okay, so again, what we can look at is notice that we have y equals in both of these. Well, just like up here when we said y equals negative 1, we could put negative 1 in place of y. Well, now we just have a more complicated thing that y equals. So we can take negative 3x plus 1 and substitute it into y into the other equation. Now we could have also taken 2x minus 7 and put it down in the other equation for y. No matter what, though, we end up getting the same equation. Negative 3x plus 3 equals 2x minus 7. Okay, and if we solve that for x, notice that we get x equals 2. Okay, so if we add 3x to each side, we'd have 5x over here. If we add 7 to each side, we'd have 10 there. Divide by 5, we get x equals 2. Okay, so that's where that comes from. Okay, so now we know that x equals 2. So now that we know x equals 2, we can substitute that value, x equals 2, into either of the given equations. So we could go up to the original and do 2 times 2 and then subtract 7. Okay, and that's what I showed you right here. Or we could do negative 3 times 2 and add 3. Okay, either way, we should get negative 3 for the answer for y. So the solution there is 2, negative 3, which matches what we said on the graph. Okay, so moving along to two examples again that we already did. Graphically, solve the following system of equations algebraically now. Okay, algebraically is the key. So we have the same 2 that we had before, and again I'm going to put those graphs up so you can see those. Okay, these are the same systems that we solved in the last one here. Okay. Now I will note that in number 2 we got both of these as y equals mx plus b, so they were easier for us to graph. It's not a very common mistake students make, or misconception, is that they always try to get y equals in each of these. The only time you should really focus on doing that is when you have to graph them. Okay, it's not necessary to get y equals in both of them and then put them equal to each other. Okay, people think that you do that and that you don't have to do it that way. It's not wrong, but sometimes it's a lot more work to do it that way. Okay, so to solve algebraically, again, the idea here is with the first one, we have y equals x plus 6 here. So in place of y, we can substitute x plus 6. Okay, so x plus 6 equals negative 2x plus 3. Okay, and then we can go through and solve that. Okay, so if you go through and solve it, answer key here somewhere. Okay, we end up, okay, I went through and solved it here. And again, if you need to pause the video and go through the work yourself, go ahead. It's just solving that equation, though. X plus 6 equals negative 2x plus 3. In the red are the steps that you do. So when you look down here, you end up getting x equals negative 1. Okay, so that's just solving this equation here. Okay, so then what you do, once you have the x value as negative 1, the whole idea is we have to find what point works, and the point is xy. So we have to find the y value that goes with an x value of negative 1. So go to either one of the original equations and put negative 1 in for x. Okay, and when you do that, I just use the bottom one, y equals x plus 6, so it's easier. So you do negative 1 plus 6, and you end up with 5. If we plugged it into the first one, you would have negative 2 times negative 1, which is 2. Okay, positive 2 plus 3, which is 5. Okay, so the solution matches up with what we had on the graph, negative 1, 5. Okay, in the second one, now we're solving algebraically. Okay, and again, we already solved this graphically, and we got y equals mx plus b in each one. And I'm going to put that answer key up here just one more time quick. When we did that, notice that we end up with a fraction in the first equation because we had to divide by 3. It is not wrong to do it this way and then set 2x minus 7 equal to 1/3 x minus 2. But then you have fractions involved, and we're more likely to make a mistake. Okay, so when you solve graphically, y equals mx plus b is a good thing to do. When you solve algebraically, getting y equals mx plus b is not always necessary, or it's not always the easiest thing to do. Okay, so to go through this example, if we look at subtracting 7 from that bottom equation, that gave us the nice equation of y equals 2x minus 7. Well, now what we can do, now that we know that y equals 2x minus 7, we could take that quantity, 2x minus 7, and substitute it in place of y into the other equation. Okay, so that's what I did right here. Okay, so we have 3y equals x minus 6. We're going to take 2x minus 7, substitute it in place of y. Okay, that's why we call this the substitution method. Well, whoop-de-doo, huh? Okay, so when you do that, remember that this whole thing right here, all this was y. Okay, so we have 3 times 2x is 6x, 3 times negative 7 is negative 21. Okay, and then we go through and solve that equation. Okay, and again, I'm just going to put the answer up there. Okay, we end up getting x equals 3. Okay, and again, if you need to pause the video, go ahead, but for the sake of time, I'm just going to keep on moving forward. Okay, so now that we have x equals 3, we know the x value where the intersection is, or the solution is. Now we need to find the y value. So you go to any equation. Now I'm going to use y equals 2x minus 7. Okay, it doesn't have to be an original. It could be one that you manipulated. Okay, whatever is easiest. And then we're going to plug in 3 for the x value. So we end up with x equals negative 1. So the solution is 3, negative 1. Okay, moving on to the next page. Okay, number 3. Okay, again, now I'm giving you hints on these. To get x equals or y equals in any equation, you don't have to get y equals in every single equation. Okay, again, that's a misconception that students have. It's not wrong, but you're more apt to make algebra mistakes if you try to do that in every single example. Okay, so what I suggest is, when you look at that second equation, if you subtract 2y and end up with x equals 2 minus 2y, now you can substitute that quantity, 2 minus 2y, in place of x in the other equation. Okay, so when you do that, you would have 3y plus 18 equals 2x. Well, now we know x is 2y. I'm sorry, 2 minus 2y. Okay, so now we just have to solve that equation for y. Okay, so we distribute the 2, okay, and then solve for y. And again, for the sake of time, I'm going to put the answer up there. Okay, we end up with y equals negative 2. If you need to pause the video, feel free to do that, but I'm going to keep moving on. Okay, and then once we found y, now we have to find the x value. So I'm going to use the x equals 2 minus 2y. Okay, because that's what, after we subtracted 2y, that's what we had for our equation for x. And in place of y, we're going to put negative 2. So right here, we're going to put negative 2 in place of y. Okay, so we do that and solve it, and we end up getting x equals 6. So the solution for the ordered pair is 6, negative 2. Now you may recall that this is the same system as on the previous. And if we were to graph each of those, again, all this work over here is really messy, but we did that in the last packet. If we graph each of those, again, we see they intersected at 6, negative 2. Okay, so that matches up with the graphical solution. Okay, so as we move on, there were 2 special cases. We're going to solve algebraically by substitution. Okay, now if we look at the first system of equations with the y equals 2x minus 3 and 2x plus 4, if we solve that system algebraically, well, notice that they're both y equals, so what we can do here, we could just take 2x plus 4 and put it in place. Okay, let me go to my other sheet here. We could take 2x plus 4, put it in place of y in that equation. So we'd have 2x plus 4 equals 2x minus 3. Okay, and then when we solve that, something very weird happens. And remember, these were special cases, so something weird may happen. If you try to solve that for x by subtracting 2x from each side, 2x minus 2x is totally gone. They cancel out, is 0. Over here, 2x minus 2x on the right-hand side is also 0. So we end up with 4 equals negative 3. Now, people get really freaked out when their x's disappear. Now, in some walks of life, having the x disappear is sometimes a good thing. In this case, what happens when the x disappears? We're happy, like usual, when the x disappears. Okay, but what happens is when the x disappears here, we end up with 4 equals negative 3. Well, another thing we could do if we added 3 to each side, we'd have 0. Oops, let me say or. 0 equals 7. Or 7 equals 0. Well, what that's telling us is that is never true. And the meaning of that is there is never an xy value you can plug into these equations where you're going to get the same result each time. Now, if we go back to the graph of these, what happened graphically was we had 2 lines that never intersected. The slopes were the same, but different y-intercepts, and what happened? They never intersect. So that's what happens graphically. Algebraically, what happens is we end up with the x's disappear, but we get 2 numbers that are not equal to each other. And again, what that means is no matter what you put in for x, you never would have gotten the same answer on each side of the equation, or the same y value, no matter what you put in for x. Again, another way to think about that is whatever you put in for x, 2x is the same number. So if x is, say, 5, you'd have 10 on each of these, and then minus 3 plus 4. Well, if you take a number, subtract 3, you're never going to get the same number as when you add 4. Okay, they're never going to be equal to each other. And again, not to belabor the point, but what that means is there is no solution. Okay, part B. If you remember what happened on this one, on the graph, what happened was we had the same line twice and resulted in infinite solutions. Okay, so graphically, that's what happened. Okay, we had the same line. Well, now, algebraically, if we look at what happens, notice in the first equation we have y equals. So we're going to take that quantity, 1/2 x plus 3, and we're going to substitute it in place of y. And when we do that, we get x minus 2 times y, which is now 1/2 x plus 3, equals negative 6. So now if we distribute that negative 2, so we do negative 2 times 1/2 x is negative 1x. And then negative 2 times 3 is minus 6, equals negative 6. Well, now what happens? X minus x is 0, and we end up with negative 6 equals negative 6. Well, we don't have to be great with numbers to recognize that negative 6 equals negative 6. Okay, I don't think we need a PhD in math to get that one right. Okay, so negative 6 equals negative 6. That is always true. And basically what that means is, no matter what we put in for x, we're going to get the same answer for y for the x value in each equation. Okay, so when that happens, again, on the graph, we had infinite solutions because they were the same line. So basically saying, if the xy value, if that point is on the line, it's going to work in both equations. Well, now what we're saying is, algebraically, this is how that shows up. Negative 6 is always equal to negative 6. Okay, so that means we have infinite solutions. Okay, moving along. Okay, so those last two were special cases. Now we're going to do a word problem, or two word problems. Okay, and I'll try to make them as quick as we can. Okay, number 5, I give you two equations that represent the percentage of women and men who are married in the year T years since 1990. Okay, so the percentage of women that are married is given by this linear equation. The percentage of men that are married since 1990 are in the M of T equation. So when will the percentage of women who are married be equal to the percentage of men who are married? And then what will that percentage be? Well, all this comes down to is solving a system of equations. So remember that W of T and M of T are just a fancy way of using function notation to say y equals. Okay, so essentially what we need to do is to set the W of T and M of T equal to each other. Okay, so if they're both y equals, that means we put them equal to each other. Okay, so I'm going to put the answer up here. Okay, we're going to say W of T equals M of T. Okay, and then you set the equations equal to each other. Okay, and they're going to be messy because of the decimals in there. Okay, but then solve that equation. Okay, and again, I'm going to show the answer up here for the sake of time. Okay, you end up getting T equals 61 when you solve that. Okay, so that tells you the number of years since 1990. Okay, so that'll be the year 2051. Now, what will the percentage be? You need to plug 61 or substitute 61 into either of your equations for T. Okay, so to find the percentage, it's kind of like finding the y value. Okay, it's like we found x, now we got to find y. Well, this is the word problem case of it. So we're going to use either of the equations. Now I just used W of T for mine. So put 61 in for W of T. So W of 61. Evaluate that and you get 47.54. Okay, so what that means, and I'll explain the graph in a second. But in the year 2051, we predict the percentage of married women and men to be equal at 47.54%. Oops. Okay, graphically, what is happening is that I put the blue line as the men. They started at 64.01%, and the women started at 59.74. But when you look at the slopes, we can see that the slope of the women is negative 0.2, the slope of the men is negative 0.27, which is saying that the percentage of men that are married is decreasing faster than the women. So that means eventually the men will decrease to where the women are, and what we're trying to find is that intersection point. So that intersection point that we found had a t value of 61, and the y value, okay, if you go straight across, the y value would have been 47.54. Okay, that's how you interpret that answer on a graph. Okay, and then the next example, okay, I give you a word problem. Okay, and I'll give you a minute to read that, or I should say pause the video if you need to read that. Okay, in part A, write an equation for the number of degrees earned by each major. So the biomed sciences started at 69.2 thousand and increased by 0.8 thousand degrees every year. So that 0.8 thousand tells you the slope. And then the 69.2 would be the starting value, or the y-intercept. And then similarly, for the security and protective services, they started at 35.3 thousand and increased by 1.5 thousand. Now notice, we're looking at the same year for each of them to start with. So that's important. Okay, so your equations, we're going to say let t be the number of years since 2006, and I'm going to use function notation, b of t for the biomed, and s of t for the security degrees, and they're going to be the number of degrees in thousands. So we have these two equations. Again, the slope for the biomed was 0.8 thousand per year, and then started at 69.2 thousand, and then the security, their slope was 1.5 thousand per year, and then started at 35.3 thousand. Okay, so those should be pretty easy equations to come up with, even though it looks confusing with the decimals and the function notation. Now we want to know, find the year when the number of degrees are equal. So this is very similar to the first one. These are both of these are basically y equals, so we're going to set them equal to each other. Okay, so we do that. Okay, and again, you may need to pause this. Okay, and solve the equation. Okay, in this one, we end up with a t value of 48.43. Okay, now this is one where you can round to 48 or 49. Okay, and this one's a little dicier than the first one. The first one, we had exactly 61 years, so no matter which equation you use, you get the same answer. Well, now the rounding will make a difference. Okay, now this is where I just need to see the work that you show. Okay, what I'm going to do is I substituted 49 into the biomed equation. Okay, so I put 49 in there and got 108.4. If you put 49 into the security equation, so put 49 in here, you're going to get a slightly different answer. Okay, because the exact value was whatever 33.9 divided by 0.7 was. Okay, I even rounded to 48.43. If you put in 48 into either equation, again, you're going to get a slightly different answer. But as long as I see what you're doing, I will give you full credit for it. Okay, so what this means, in 2055, we expect 108.4 thousand degrees in each program. Okay, and again, graphically, we can see what's happening on that. The biomed started at a higher value, 69.2. Okay, so that was the red equation here, or the red line here. And then the security started at 35.3 thousand, but the security has a larger slope than the biomed, so that means that the number of security degrees are increasing faster. So eventually, because the slope is larger and more steep, eventually the security will catch up with the biomed. Okay, and when that happens, the t value there is approximately 48 or 49. Okay, so that's it for that lesson.